Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Maxwell West, who will tell us about real classical shadows. So Max is a PhD student at the University of Melbourne, and his main research interests are in basically the use of tools of representation theory and random matrix theory to help explain sort of quantum systems and algorithms and characterize their function. So Max, the floor is yours.
Oh, awesome. Yeah, so thank you very much, and thanks for the invitation. This is cool. All right, yeah, so I'm gonna today talk about some work I did with my genuinely really amazing collaborators. I know you have to say that, but yeah, these guys are, are sort of all really awesome. It's Antonio Anamile from FU Berlin, and Martina Rocca and Marco Cerezo from Los Alamos. And I might also just quickly say, so this work came out of the quantum computing summer school that Los Alamos does every year. So if there are any students, I would definitely recommend you apply for that. Although I don't know, maybe the deadline has passed for this year, but yeah, I think it's every year. It's really cool. All right, so I guess I was asked to sort of maybe start pretty slowly. I think I understand there's a lot of sort of variation in how much people in the audience might be familiar with all this. But basically, I'm going to talk about classical shadows, which is this sort of really cool, really powerful framework that sort of appeared for learning about unknown quantum states over the last few years. And I'm going to hopefully go through that sort of fairly thoroughly to the point to where we get to this so-called real classical shadows that we have introduced in this work. It will hopefully be pretty clear why you would expect the sort of thing that we do in this paper to be possible, which is namely sort of taking the general framework of classical shadows and then sort of specializing it to target a certain set of properties. And then, yeah, basically, as we'll see, you can do that. You can make these sort of specialized instantiations of the general theory that sort of outperform other protocols, for some specific set of properties. And yeah, so we'll hopefully, come to understand why we would believe that should be possible. And then, yeah, we'll see it in this example here. Oh, also, so I'm not sure what the policy is with formality, but yeah, I'm definitely very happy to stop it at any point if anyone has any comments or questions. Okay, so to start kind of right at the beginning, I suppose, this is all about trying to learn to characterize unknown quantum states, which is, say, d-dimensional and completely unknown. Maybe it's pure, maybe it's mixed. It could be anything. And then the sort of fundamental problem is that, to learn about these systems, we want to sort of extract the classical information from them somehow. But then measurement famously is this sort of destructive process that in general is just going to mess up your quantum state, right? So it's not necessarily true that will happen, right? So if you measure an operator with respect to which your state is already an eigenstate, then it doesn't change. But of course, the problem is the word unknown, right? So every time you make a measurement, you're in danger of sort of measuring some observable with respect to which the state is sort of right on the edge of being sort of maximally uncertain about. And then you essentially just completely destroy the state. So then, okay, the lesson is we need lots of copies of the unknown state that are maybe being prepared on a quantum computer. So maybe you even have the source code of the unitary that's creating the state, but it doesn't necessarily imply that you actually understand the state particularly well. Or maybe it's, I don't know, it's coming from some quantum sensor or something more exotically. Okay, anyway, so perhaps I guess the first sort of natural option is you could just do quantum state tomography, right? Which is going to sort of give you an exact classical description of rho. But then the problem is the scaling is sort of pretty horrible. So you would expect at least sort of a lower bound of d squared, because remember, this can be a mixed state, so it's a sort of something like d squared dimensional object. And this is a sort of type bound. It's exactly d squared. And then, of course, this just is not scalable at all because the dimension of the Hilbert space, if you have, say, like a qubit system, or I mean anything else really, tends to scale exponentially in the size of the system. Actually, so even just like last week, I was talking to someone who was trying to characterize a state that he'd made on like 20 qubits. I mean, it's horrible, right? Like 2 to the 20, and then you square it. That's that's not very friendly. But all right, so then that's sort of like full quantum state tomography process that produces the sort of full exponential amount of information is in general going to be overkill, right? So in many applications, what you actually care about is a sort of list of somehow simple properties of rho. And you would expect, well, or maybe hope, that for certain definitions of simple, I mean, it shouldn't take you like an exponential number of copies to extract this from any state. And this intuition is, I believe, actually one of the things that sort of motivated Scott Aronson originally when he was thinking about this. So to be concrete, suppose we have like some list of capital M operators or observables with respect to which we want to know rho's expectation value. So okay, again, in general, like these guys fail to commute, so you can't simultaneously measure them. And the sort of knowing about one is sort of messing up its properties with respect to the others for a given copy. But okay, I mean, you can sort of group them into sort of commuting cliques and then measure representatives from each clique individually. Or I mean, even without doing that, if there are M of them, you can just measure them like one at a time, right? So then this sort of reveals by definition only the properties that we've declared that we care about. And the sample complexity is now just linear in M. But I don't know, I mean, so in some sense, this is kind of a sad way to live, right? Just sort of measuring everything one at a time. And in particular, if you're doing this, we're somehow not learning about the stuff that we've already seen, right? Every time we get a new observable, we just measure it again. And so maybe one can do better. And the kind of big result of the theory of classical shadows is that I mean, one can actually do sort of dramatically better and actually sort of exponentially reduce the sample complexity with respect to the number of operators that you'd like to learn. And so I thought, I might actually just sort of write out exactly sort of what the steps are and what's involved, because I think it's not so bad. And then this is going to put us in a position to actually, to have a little bit of intuition about how we could improve the general procedure in specific cases. Oh, okay, let me also maybe just say sort of just quickly, I'm going to focus on kind of the simplest setting where we just measure the copies of rho one at a time. And we do this sort of independently. So we don't let the results of earlier measurements sort of affect our choice of future measurements. So you can relax both of those assumptions, but we don't in this paper. All right, so having made these sort of simplifications of saying we're just going to measure one copy at a time in a sort of non-adaptive way, these protocols are defined basically by two choices. You pick an ensemble of unitaries, by which I just mean like some set of unitaries with a probability distribution over it. And you pick a basis of the Hilbert space to measure it. And then there's this kind of multi-part process where what you do is you take one copy of your state at a time, and then you sample from your distribution of unitaries and evolve the state, getting some, Euro U dagger, and then you measure this state, which is going to randomly produce some W. And then so this word store is maybe a little vague somehow, but you sort of classically sort of store or remember this state, which is the adjoint of U acting on W. So in particular, I mean, you never need to prepare this state on a quantum computer or anything. You do two things, right? You sample your U's, and then you measure and you get some W. And then with this combined information, you somehow write down this state. And so then if you think about it a little bit, what this is doing, sort of in effect, is carrying out this quantum channel, which we'll call the measurement channel M. So you put in a row, and then the objects you get at the end of these you dagger WWUs. And then this is just basically adding up all the things you can get and weighting them by their probability, which is maybe even a bit clearer if you sort of cyclically permute this copy of U around. I hope my mouse is visible, by the way. Yeah, you take this copy of U at the end and sort of wrap it around. This quantity here is the probability that you produce this final state, having carried out this little procedure. And then you add up all the possibilities. And this is the measurement channel. Sorry. All right. So we got a bunch of these pairs, U's and W's, that we get sort of at every step of the process. And then there's one more step where we take these states and apply to it the sorry the inverse measurement channel M. And then this sort of total object we call a classical shadow of rho. So here, I guess there's kind of two things to immediately say. The first is that in general, M is not actually going to be invertible. So this is going to be the pseudo-inverse, or just the inverse on the image of the channel. And then the second thing is again, this is not happening like sort of on a quantum computer or anything. You're not actually trying to implement this channel and apply it to a real quantum state. And indeed, in general, this channel is not even going to be unital. So you couldn't implement it sort of even, sorry, it's not CPTP. So you couldn't implement it like in a real quantum system, but this is all just happening classically. Okay, and then the really cool thing about these rho hats, these classical shadows of the initial state, is that you can use them sort of as proxies for the state itself. And in particular, use them for the process of estimating expectation values in even just a sort of like just a generic sort of empirical average type of thing, where instead of taking our target observables and contracting them with rho, we just contract with the shadows one at a time. And all right, so here there's again maybe two things to say. First of all, in practice, there are sort of cleverer things that one can do instead of just taking this empirical average. So in particular, the original classical shadows paper talks about this median of means approach, where you sort of like bin your samples into like different sort of subsets, take the mean of each subset, and then your final prediction is just like the median of all those means. And this has sort of some nicer statistical properties somehow. But I think that's maybe for us, that's not so important. It's a kind of implementation detail. The bigger question is the use of this approximation sign and whether we actually believe this. Because just at least if this is maybe the first time like you see this, it's not obvious necessarily that this sum is actually going to converge to these true expectation values, right? So all these things, these are hats. These are like independent, identically distributed random variables. So this sum is certainly going to converge to something, right? In a central limit theorem sort of sense. But we're certainly concerned about whether it's actually going to converge to the true expectation value. And well, also how long it's going to take to converge. Okay, yeah, so this is basically what I was just saying. We're worried that our estimates that the shadows are going to give us may or may not be converging to what we want them to converge. And I mean, even if they are going there, what's the rate of convergence? And this rate is super important for us because this is basically going to tell us the sample complexity of estimating these operators. Because, we've got this central limit theorem little picture in our heads where all the estimates in total are making a little Gaussian around hopefully the true value. And then depending on the variance of that Gaussian, we're going to need to take different numbers of samples before we're confident that we've actually converged. And what we're going to see in a second is that the answers to both of these questions depend on both of the choices that we make. So remember, we pick a unitary ensemble to sample from and a basis to measure in. And these define our specific classical shadows protocol. And they're gonna inform the answers to these questions. Okay, so first we make one more definition. I don't know, probably doesn't really need to be a definition because we already have a name for it. But we define the visible space of a shadows protocol, which depends on our two choices, just to be the image of the measurement channel, which, now that I think about it, probably this measurement channel could have like a subscript like U and W to indicate that dependence. But anyway, we call the image of the channel the visible space of the protocol. And if you sort of unravel the definitions a little bit, this is just the span of these guys. And what one can show, and this is, again, basically a matter of sort of unraveling the definitions, is that these O hats from the previous, no, from 2 slides ago, well, they were on the last slide too, I guess. Anyway, the O hats converge to not necessarily these true expectation values, the trace of rho times O, but the true expectation values of the O's if you project them onto the visible space. So this is maybe more or less believable, especially if you remember these shadows are coming, that when we define the shadows, there was an M inverse of these things, right? And so the bits that are not in the span of the operator, that are not in the image of M, they just don't get seen. They get annihilated by taking this pseudo inverse of the measurement channel. Okay, we'll see some examples of this in a second. But for now, I guess the key sort of running piece of information is that a classical shadows protocol is defined by these two choices. And what we've seen so far is that for specific choices, you may or may not be able to estimate given target observables. Okay, so that was kind of the. Oh, sorry. Yeah.
Can I just ask a question? Do you mean the measurement channel acting on O is in the visible space, or O itself is in the visible space?
Oh, sorry, I might have said that wrong. Yeah, definitely O is in the visible space.
Okay.
Yeah, so I think so something that's maybe it will be, I don't know, maybe makes things a little clearer. So these, sorry, you can see the mouse, right? The pointer.
Yeah.
Good. So we get estimates that look like this. So if you imagine this rho hat, you can put like a little M inverse, of this thing here. And then the measurement channel turns out to be like self-adjoint with respect to the Hilbert-Schmidt inner product. So you can then like move this M inverse sort of around. And in particular, it can hit the O. And then if O is not in the image of M, then like M inverse just annihilates it. Right, because it's really the pseudo image. Oh, sorry, the pseudo inverse. If that, yeah, I'm not sure if that's helpful. Okay, cool. All right, so we have a bunch of observables that we want to estimate. Some of them we can't. So we can only estimate, or at least without bias, we can only estimate operators that live in a certain subspace. And okay, sorry, maybe one more thing I should emphasize. So this visible space, it might actually be the whole operator space. And sometimes that will be true. But in some sense, the more interesting protocols are the ones where the visible space is actually a strict subspace of the whole operator space. Anyway, so that's kind of question 1. And then question 2 was about how quickly our variances, how quickly our estimators actually converge to, whatever they're converging to, whether or not it's the exact estimate or not. And again, we have this kind of like central limit theorem sort of picture in our head, hopefully, where these things are forming a Gaussian. And then the number of samples that we need to take in order to be with some high probability that's been hidden by this big O notation, within an epsilon sort of error is going to be a function of the variance of these estimators, right? So if the variance is too big, then the Gaussian is really wide, and it takes you maybe a long time to be sure that on average you're actually doing the right thing. This result, okay, this is certainly not immediate. This is you derive, or one derives all of this. So I think, all right, so the epsilon squared down the bottom, this is coming from a sort of standard Hofstad's inequality type thing. So for some like fixed error and for some fixed probability, you can just sort of absorb all of this into the O. The variances we've talked about. So I think hopefully this makes sense. And then the thing that's really big that, well, sorry, there's not really big, that's really small, that kind of makes all of this work, is the fact that M, which is the number of observables that we can estimate, actually enters like only logarithmically. So this is, and this is kind of awesome. This is again actually basically coming from this Hofstad's inequality type thing, right? So you want all of these, you want the probability that everything that a given observable is estimated well to be, oh, sorry, let me say it again. You want the probability sort of failure for a given estimate to be less than like sort of 1 on M, right? So that you can estimate M things and probably get them all right. And then what the central limit theorem essentially is doing here is saying that like variations away from the mean are being punished exponentially. So that's where basically the M just gets hit with a log. So this is super cool. This log M is independent of our U's or W's or anything. But the problem is, for the potential problem, is like this variance term is not innocuous. So this by itself can easily be, say if you have like an n qubit system, these variances can be exponential in the number of qubits. And then the fact that you've sort of done all this cleverness and made the dependence on M only logarithmic is not really worth much if this term turns out to be, exponential, and you're sort of kind of back where you started. So then what we want to do, and what kind of the game is to, like, given some target observables, pick a U and a W that makes these variances small. Oh, and also that ensures that the O's are actually in the visible space. And then if you can do that, see if this is like polynomial in the system size, then yeah, this is kind of incredible, right? This is kind of, yeah, justifying the title of the paper, where you make like a relatively small number of measurements and can estimate, yeah, like a number of things exponential in the number of samples that you take. Okay. So, sorry, we're nearly at the new stuff. But just to give maybe a bit of an example of this, so in all these cases, we'll just take W to be the computational basis, and then we'll see what happens if you make different choices of U. So for example, if you just sample uniformly randomly from the whole global Clifford group, and you sort of go through and do like the Weingarten calculus and so on, you can show that these variances are bounded by the 2 norms per squared of the operator. So if your operators have small 2 norm, so for example, like projectors onto small subspaces, or measuring fidelities with respect to different states. So here the 2 norm is just 1, right? So for these sort of observables, yeah, you're great. The variance is bounded, and also for global Cliffords, one can show the visible space is global. It's everything. But there are certainly sort of interesting observables that don't have small 2 norm, right? So for example, like every Pauli string that has a 2 norm that's 2 to the n. 2 norm, yeah, there's this 2 to the n, well, it's exponential. So the global Cliffords, yeah, just can't do them at all, or at least they take exponentially many samples. But if you instead take U to be random local Cliffords, so these are, say, single qubit Cliffords acting independently on each qubit. So every time you do like a sample, every qubit gets a different or at least a randomly sampled local Clifford. There are, I guess, not that many of them, so some of them will be the same, but but yeah, they're independent. And now you see the variance behavior, it just changes completely. So with the global Cliffords, the only important question is, is the true norm of my operator, large or small? And now it becomes, is my operator local spatially? So for example, if you just take your operators to be just Pauli strings of some given support, where by support I just mean, it's like acting non-trivially on exactly k qubits, then you can show that the variance, is bounded by 3 to the k. And if you relax that a little to just take arbitrary operators that only have support k, then the bound goes up to 4 to the k. We'll see a little in a minute where these numbers kind of come from a bit more intuitively, and also how they change when we do real shadows. But this, I'm just trying to emphasize, this is like completely different behavior, right? So in particular, this is independent of the total system size. And then is a kind of another different example. If you take U to be the so-called fermionic Gaussian unitaries, or indeed their intersection with the Cliffords, excuse me, then the variance turns out to be bounded by the so-called fermionic degree of the things that you're measuring. I don't know. So maybe you don't want to, this last example, I guess, may or may not be too familiar. I didn't want to belabor it too much, but I just bring it up because these fermionic observables that are basically mapped from the Pauli strings by like a Jordan-Wigner transformation, you can have those observables like this that have like so-called low fermionic degree, but that sort of completely fail both of these first two conditions. So they can be Pauli strings that are like have support everywhere. So their two norm is really big. Their k is like n, so it's also really big. But if you sort of make the right choice of unitaries, that's sort of somehow taking advantage of the fact that these are in a certain sense sort of local, like not spatially local, but somehow fermionically local, then again, you can get a really good variance found. So in this case, this is like some polynomial of degree k. Okay, so I think, one more slide, I think, before we get onto it. So I guess I keep saying that we have this dependence on U and W, but I didn't say exactly what this dependence is. And it turns out, maybe a little surprisingly, that this dependence is sort of exactly encapsulated by this expression here, where k equals either 2 or 3. So it's kind of like an average with respect to both with respect to everything, right? You're averaging sort of over the ensemble, and you're asking how does this sort of adjoint action of my unitaries behave on average on the computational basis states that we're measuring it. So in particular, this kind of explains a little why I kept saying Cliffords in the last few slides instead of say like random unitaries, because the Cliffords are a unitary 3 design, if you're familiar with that, which means that, there's sort of no benefit to using proper random unitaries for shadows, because the shadows are somehow only probing sort of quadratic and cubic moments. And not only that, they're only probing these moments on sort of rank 1 objects. So this is maybe a little reference to a sort of a different paper that I wrote with the same people, basically in parallel with this real classical shadows. So originally we were trying to work out what do the classical shadows protocols look like for the orthogonal ensemble, which I'll get to in a second. That's the real classical shadows, and also the symplectic ensemble. So this is just a different distribution of matrices that have certain properties. They preserve a so-called symplectic form. And what it turns out is that if you do this integral over the symplectic group, in general, the k-fold averages are sort of completely different. It's just a different ensemble. But if you only act on like rank 1 things, like states, it turns out that this integral, or this expectation value, is actually the same for the unitary group and the symplectic group. So this is kind of, I don't know, it's independently a little interesting. I think a nice way to think about it to say it is if you have like random like unitary matrices or symplectic matrices, and you only look at individual columns, you sort of can't tell the difference. The columns being these like random states. Like the only difference is in the correlations between the columns. So I don't know, that's pretty cool. Except in the case of classical shadows, where it means that symplectic shadows are kind of boring because the dependence enters only in through this term, and this term is the same for symplectic shadows and full unitary shadows. But it's not in general the same for the orthogonal group. Okay, so now I guess we come finally to the real classical shadows, where hopefully at this point this is all sort of pretty well motivated. So by taking different ensembles, we can get shadow protocols that, as we saw, behave like completely differently, and the operators for which they're good for really do like very strongly depend on what the ensemble is that we're sampling from. And so by real valued, or by real classical shadows, yeah, we're just going to mean a subgroup of the orthogonal group. And sort of a real valued measurement basis. And we'll relax this measurement assumption right at the end. And we'll see actually something pretty cool. That's not completely in the paper, actually, that I just sort of realized a few days ago. But okay, so one more, I guess, just sort of quick comment before we look at it. So it turns out that if you restrict the Cliffords to the orthogonal group, then they form a 3 design. The orthogonal Cliffords form like an orthogonal 3 design. So up to the third moment, you can't tell the difference between random orthogonal matrices and random orthogonal Cliffords. So throughout this, yeah, when I say random orthogonal matrices, I could just be talking about Cliffords, which is super important for actually trying to implement any of this. Okay, so I guess the situation is kind of summarized, at least on the bottom part of this little figure here. So in the unitary case, well, I guess we didn't see, but we asserted that the visible space is kind of maximal. So with unitary shadows, you can see everything, but sometimes the variance is going to be really bad. If you take the symplectic group, okay, it's just the same as the unitary group. So again, you see everything, but sometimes the variance is bad. And then, as we'll see in over the next few slides, if you take the orthogonal group, the behavior is kind of qualitatively different. So the visible space is now smaller, which means you can't see everything. So I guess the little cartoon here is if you sort of sample something from outside the visible space, it's going to be, the estimates that you get are going to be biased. I mean, okay, this picture is maybe a little misleading. If it's literally orthogonal to the visible space, you'll just get 0 every time. Anyway, if it's sort of not completely aligned with this subspace, you just get a biased estimate. But if it's in the visible space, not only do you get an unbiased estimate, but the variance, as we'll see, it's going to be smaller, which this cartoon is trying to indicate. So you can't see everything, but for the ones you can see, your sample complexity is going to be improved. Okay.
Sorry, can I interrupt?
Yeah, please.
Yeah, no, I mean, just out of curiosity. So this thing that you mentioned about the real Cliffords, so I think Cliffords form a unitary tree design. So does the real Cliffords being orthogonal tree design just follow from this property, or not exactly?
I don't think so. I think it's not obvious.
Oh, it doesn't necessarily follow.
I think so. For I don't know. Maybe it should be obvious, but it's so not only is it not obvious to me, and for example, if you ask the same question about the symplectic group, like are the unitary symplectic Cliffords a unitary symplectic 3 design? I don't know what the answer is.
Oh,
So
okay.
I think it's not obvious.
Okay.
Yeah, sure. Thanks.
Sorry, can I just clarify what do you mean by real value W? You might have said it and I missed it.
Sorry, no, that's absolutely so I was supposed to say that. So this is kind of like just literally this is a weird thing to say, right? Like in particular, if you just multiply like your basis vector by a phase, that shouldn't change anything, right? So what I more strictly mean is that it's every one of the vectors is linearly dependent with its complex conjugate. So this, okay, sorry. So this is also technically maybe a slightly weird thing to say. So when I say the orthogonal group, I mean the matrices that satisfy O times O transpose equals the identity. And so this is not like a basis independent thing to say, right? If you can do like unitary changes of bases, then this orthogonal group, they literally, it's a basis dependent thing. So having fixed like some instantiation of that, I say like with respect to the computational basis, I want OO transpose to equal the identity. That fixes a basis. And now we can say in that basis, I want my vectors to be proportional to the complex conjugate vectors, which I declare to mean real valued.
Thank you.
Okay, thanks. Yeah. This is an oversight. I should have said it. I should have specified this at this point. Okay, thanks. So now at this point, yeah, I mean, we just sort of, you can, so these measurement channels, if you remember, this was just like some expectation value. So it's like a twirl over the orthogonal group of some different things. And at this point, you can basically just do this fairly standard Weingarten calculus sort of thing. And just, yeah, just work out everything, work out the channel and the variances and so on. And so what we see is I think kind of cool. So this is the answer just from doing the integral. And we see that it's a depolarizing channel on the sort of symmetrized version of whatever you put in, this A plus A transpose thing. So in particular, if A is anti-symmetric, oh, I'm sorry. So again, this is like transpose is like basis dependent, right? We've fixed a basis. So if A is anti-symmetric with respect to this basis, then the channel just annihilates it. So then it's not in the visible space, right? Which is the image of the channel. And the visible space is exactly the things that are symmetric, because the anti-symmetric component is always just being annihilated. So that's already kind of maybe a little bit different from the unitary case, where nothing gets annihilated. And what's also cool is if you remember from a few slides ago, the variance with like global unitaries or global Cliffords, the bound was just the 2 norms squared of the operator. But here we get this extra factor of a half, which is basically, if you then put that into our sample complexity formula from earlier, where the variance is just entered just like multiplicatively, this is basically just saying you only need to take sort of half as many like samples to get the same level of confidence that you would if all you care about is symmetric matrices. Okay, so that's, I don't know, that's maybe kind of cool, but it's sort of only a constant factor, right? And if we go to the analogous version with local real shadows, so now we're like on each qubit acting independently with local real valued Cliffords, the difference is a bit more dramatic. So we project onto, I mean, I don't know, I don't really love this name, but I guess it's my fault. But we call like the sort of locally symmetric operators, which I don't know, basically just means write everything out in Pauli strings and then just delete any string that has a y in it. So basically, you know, if you look at any qubit, it's just I, X, and Z. So it's just the symmetric ones. Basically, just on each qubit, your little like local orthogonal Cliffords are just killing all the anti-symmetric stuff, which is just proportional to y. Anyway, okay, so this is the visible space then, just all the Pauli strings that don't have a y in them. I also just noticed I don't think I've been too careful or consistent with whether I'm saying real span or complex span, but okay, it doesn't matter, I guess. Anyway, so if you remember again from a few slides ago, in the unitary case for an arbitrary k local operator, the variance bound was 4 to the k, and for a arbitrary Pauli string of support k, the variance in the unitary case was 3 to the k. So in these cases, now our variance bounds are, yeah, sort of improved quite a bit more significantly, right? This term that is sort of growing exponentially in k. So this, yeah, I think this is kind of neat. This is basically like the trade-off, right? So with unitary shadows, you can measure a lot more than we can with these local orthogonal shadows. But if you happen to care about things that are in this span, which I don't know. So I'm told, my understanding is you can come up with certain examples in, say, condensed matter physics or something where you have Hamiltonians that produce, these real valued terms. Anyway, if you do happen to be in that situation, these improvements are, potentially a bit more dramatic. Okay, and then this is, I guess, formalizing that a little bit, just in the case of Pauli strings. So say like you don't do any like random, you skip the step with like the U's, right? Or you just take your distribution to just be the identity, and then you just measure in, say, some basis. Then what that's going to tell you about is the operators that are already diagonal in that basis, right? And then you can think of it as these randomized measurements, or these random like Cliffords or whatever, as basically just changing the set of operators that are diagonal in the basis that you're about to measure in. And then intuitively, what you might expect is that the number of samples that you're going to need to take is to be somehow sort of proportional to basically the number of times you have to run things before every operator has been diagonalized, at least some constant number of times. And this is basically just sort of noting that this is actually what we see. So if our target is these operators, just the spans of x's and z's acting on, non-trivially on k qubits, then you hit this with some random local Clifford, and given like some target string in there, the probability that your random local Clifford diagonalizes it is 2 to the minus k, which is exactly 1 on the variance that you get with the corresponding shadows protocol. And this is a bit more sort of, I don't know, maybe a bit, well, it's the same thing, but in like this fermionic case, you sort of have more than one term that's sort of visible, or sorry, that's diagonal at a time. This turns out this is coming from the sort of the number operators, the A dagger A's in the fermionic picture. Anyway, so I guess the time is sort of ticking along, but I think this is kind of a bit of a cool little last thing. So if you take orthogonal shadows, this, okay, so I should have had this equation earlier, I guess. But if you take the orthogonal shadows and then just drop this sort of reality requirement on the basis vectors, what we find is that when you go through everything, the protocol, the only dependence of the protocol on W comes in through this quantity here. So this is just the average over the basis of the overlap between the vectors and their conjugates. So for example, in the original case, the real shadows case that we were doing before, these numbers were always 1, and there's d of them, so f was just 1. And then if you go through, now the calculus is a bit yuckier, but you can sort of go along, and you find that you get a depolarizing channel on this now general linear combination of A, and A transpose. So if f equals 1, like in the real shadows case, this is just A plus A transpose over 2, which is what we were doing before, what we got before. But if f equals 0, then you don't see the transpose anymore, and this just becomes a depolarizing channel on A. And so, despite the fact that we're now doing everything with like orthogonal Cliffords or just orthogonal gates, we actually recover the full unitary shadows, which I think is surprising. Although, okay, so at this point, you could object, how do you know that actually such a basis exists that does have f equals 0? And it turns out, okay, if you search for a little while, you can find a basis that satisfies this. And it's actually, interestingly, it's actually like super easy to construct, like at the circuit level. So if you just take, like, say, the computational basis, you hit everything with Hadamard's, and then, oh, sorry, I forgot to write it down. This S, this is like a phase gate. This is like 1 and I on the diagonals. And if you do that, you not only get a basis that satisfies this sort of 0 reality condition, you actually find that if you do the integrals for any of these y's over the orthogonal group like this, or over the unitary group, you get the same thing when k is less than or equal to 3. So this, I don't know, to be honest, I wouldn't claim to massively understand this like intuitively, except insofar as the next slide sort of helps a little bit. Oh, but before I say that, so if we recall, the dependence of the shadow protocol on our ensemble and on our measurement basis was basically through exactly this quantity when k is less than or equal to 3, right? It's actually even a little bit weaker. The dependence is on like the sum over y of these terms, but I mean, they're equal for every y, so the sum is also equal. Okay, so this is the last slide, I guess. I think this, I don't know, so this is not in the paper. I just sort of thought of this a couple of days ago, but I think it's kind of cool. And the idea is to try and look at the difference in behavior that we saw with these real shadows, with the real basis, and this sort of like, I don't know, completely complex basis from the last slide. And so the idea is to look at the decomposition of like, say, and h. This is just all the linear operators, the space of linear operators on our Hilbert space, to look at how this decomposes under the adjoint action of the two different groups. So I don't know, maybe we don't need to belabor massively exactly what's going on in these pictures. But basically the idea is that the different connected components of these graphs, I should say also there's like an imaginary line. The green and the pink line at the top, this is just a completely different object from the orthogonal case down the bottom. So in the top component, this is sort of like a visual, I don't know, an attempt at a visual decomposition, a visual, well, it's a visualization of how the operator space decomposes into irreducible modules under the adjoint action of the unitary group. And so what we get is that every one of these like vertices of the graph is supposed to represent, I don't know, hopefully you can read this. I guess you can. Every one of these vertices is supposed to represent like the span of a Pauli string. And then the connected components live in the same module with respect to the action of u. So in the unitary case, the identity sort of lives by its own in this trivial one-dimensional representation, right? This is always true. And then it turns out that all the other operators, they all live in the same module. But in the orthogonal case, if you, and this is just, you do maybe a little bit of representation theory or so, and you sort of ask what's the decomposition into modules, you find that actually there are 3 components instead of 2. So the identity is always by itself in a trivial representation, but you find that this big module actually splits up into 2. And then this is kind of maybe giving us, I mean, I don't know, at least a little bit of intuition of what's going on. So these 2 modules, it turns out, are spanned exactly by the Pauli strings that have either an even or an odd number of y's in them. So this blue one, if you look at the various strings, unless I mess something up, they should always have an even number of y's. And this yellowy gold one should always be an odd number of y's. And then if you, sorry, I'll just go back just for a tiny second. We care about these objects, right? These orthogonal or unitary groups acting in the adjoint representation on these basis states. But then, I mean, like, what do these basis states actually look like? So if it's just like the computational basis, these guys are always in the span of just i's and z's, right? But that means there's no y's in these strings. And in particular, I mean, there's always an even number of y's, right? It's just 0. So the action of the orthogonal group on these w's always just stays within the blue component. But if you use this alternate basis, right, with the Hadamards and the phase gates, these w's basically become an equal superposition over the same thing, but with the z's replaced with y's. And now if you expand this, you get even and odd numbers of y's, right, from different strings, which is, I think, is maybe it's a little neat. So now this evolution is not just sort of restricted to one module anymore, right? It's sort of over both of them. It's still not exactly the same as evolving over like this full green module, right? Because the two, the different parts of the people, in one module still can't talk to the other one. So it's not exactly the same. And it turns out the extent to which it's the same is just up to the third moment, which is exactly what we want for the shadow protocols to be equal. Yeah, I don't know. This is maybe just a bit of intuition. I think this is kind of neat. Okay, so I guess that's basically the end. So I think hopefully the moral of the story was hopefully was conveyed. is that these classical shadows is sort of a general framework that you can instantiate for different purposes with like different choices. And these choices in general let you target specific sets of observables and lets you learn them more quickly, sort of at the cost of not being able to learn other ones. And in particular, what you would like is distributions that kind of just sort of act on and only on sort of adjointly spaces of the observables that you actually care about. So for example, if you only care about, Pauli strings with x's and z's, you want an ensemble that doesn't act on them and sort of produce y's. And that's what the orthogonal, exactly what the orthogonal ensemble does. So yeah, thanks for coming, I guess.
Okay, thank you very much
Thanks.
for a splendid and very informative talk. So yeah, so I guess we have maybe like a few minutes for questions. So anyone who has questions, feel free to just unmute yourself and ask them right now.
Hi, yes, I actually have a question. So first of all, thank you for the nice talk. And so you're saying that you have a certain interest of the observable in the subspace, and you try to sample from a smaller subspace of the measurement basis, so you get more hits, right? Is that the case?
I think I didn't quite hear like everything, but yeah, basically you want your ensemble to only sort of map operators amongst themselves in the subspace in which you're interested. So if you take like x's and z's, sorry.
Yes, sorry, please go on.
Oh yeah, sorry. So say you only care about Pauli strings with x's and z's in them. If you use like just arbitrary unitary like local Cliffords, the action of that on the x's and the z's is going to introduce y's, right? So the sort of like the subspace is bigger. The subspace is like it's mentioned 3 to the k thing, and you're going to need of order that number of shots to resolve everything. And so this is more informative, right? It tells you about the things with y in them too. But if you don't care about them, then you just want to stick in like as small a subspace as possible that only has the things that you care about.
Yeah. So I'm thinking about there's also a de-randomized version of classical shadow, right?
I believe, yeah, I honestly, I can't sort of really comment on that straight off the top of my head. I have seen it and I've been meaning to read about it. But yeah, there is. Sorry.
Okay. Thank you.
Thanks.
Do you see this procedure as being like generalizable to a situation where you have kind of a specific subspace that you're interested in of observables? Do you see a way of kind of defining the ensemble and measurement basis to target that specific subspace in a kind of minimal way to minimize your sample complexity?
Yeah, I think so. So I guess this is like a sort of a representation theory question, right? It's like given some subspace, is there a group that sort of naturally, acts irreducibly on that space? So I think we have a little bit of stuff that we're trying to work on in that regard. But yeah, I think so. To be honest, it's easier just to pick a group and sort of see what it does than do the sort of the inverse question, just kind of what you're asking. But yeah, definitely that's kind of the goal, right? To have some target. And then, I think it's a question of trying to come up with a group that acts irreducibly on that subspace. Yeah, I don't know if that's sort of possible in general or tractable.
And maybe a motivation question as well. Have you guys thought about settings of like applications where this is useful?
Yes, so I think I forget, maybe I mentioned it briefly. So I think Marco Cerezo at some point mentioned that he's aware of some Hamiltonians or some like condensed matter systems where these are the strings that you do care about. Or I think also maybe even like IQP circuits or something. Then maybe you only care about X's and Z's. But beyond that, yeah, I'm not super sure exactly, yeah, when you would care. I think, yeah, my understanding is this example does exist somewhere in condensed matter physics.
Right. Okay. I mean, I just wanted to follow up because I sort of had a similar question. I mean, I understand that, as you say, it's easier to start with the group and just see what happens rather than like. But what came to my mind is, for example, so let's say like I have this. They have this something called the pseudo-random states, like set of states that are computationally indistinguishable from random states. So, like, there's some results about it where basically, in order to distinguish it from random, you basically each state is the observable that you want to try to be able to determine whether, yeah, that's the thing that you want to be able to determine. Because in some sense, like you want to do some measurements where do I get an expectation value of 1? And then that would mean that I'm getting one of the observables, and that I mean I have one of the states. So in that sense, like it's kind of natural that what I really want is like I know the observables, and then I want to be able to choose the correct unitary ensemble for it, right? Sort of like do it backwards. But I understand that this is like a more complicated question.
Yeah, exactly. So I think, so something we're developing at the moment that I think, I mean, it still doesn't answer the question, but it at least kind of automates it a tiny bit, is trying to just understand like very automatically, if you have a group, like what's the channel going to look like without going through all this Feingarten calculus stuff and trying to do all the integrals, just have like a general framework that does it all. But it's still, it's still not really answering the inverse question. It's just answering the first question, but faster, I guess.
Yes.
Yeah.
Okay, but maybe let me just ask a different question then. So, but given observables that I'm interested in, is it immediately clear that I only need kind of the real version of classical shadows and not? Is there like something to guide me to make this decision?
So in this specific example, it's just the question is, do the observables, I guess, satisfy these conditions? So more generally, it's does like the subspace that they generate form like an irreducible representation of some group? I honestly, I don't know.
It always goes back to that question, right?
I think so, yeah.
Sure.
To be honest, I think I'm not even really answering the question. I'm just sort of rephrasing it a little bit. But yeah.
Yeah, but at least this gives sort of like the idea that maybe one can sort of refine it to do sort of like something more for a specific use case.
Yeah.